Welcome to The Explainer. Today, we're taking a deep dive into the microscopic mechanics that actually make modern industrial robots possible. You know, when you see a massive robotic arm assembling a car, or, say, performing a delicate surgery, that smooth, flawless motion, it honestly seems like magic. But, spoiler alert, it's not. It's just highly advanced mechanical engineering. So, we're going to unpack the cutting-edge science of tooth surface modification in harmonic drives. It is, quite literally, a revolution in robotic precision.
So you gotta ask yourself, how exactly do robots move with such perfect, repeatable precision? Well, to really understand this, we have to scale way down, resuming right past the macro level of that giant robotic arm, straight down to the micro level of the gear teeth hidden inside its joints. Because believe it or not, this is where the real heavy lifting happens. Okay, let's dive into this. The beating heart of these robotic joints is this incredible mechanism called a harmonic drive, or strain wave gearing. It's a completely unique mechanical gear system. Right, instead of rigid gears just clunky spinning against each other, a harmonic drive uses a flexible spline. Think of it like a cup with external teeth that's repeatedly stretched and deformed by a rotating elliptical plug inside it, which we call the wave generator. As it stretches, those teeth engage with the internal gear teeth of an outer, rigid spline. It's just this brilliant, dynamic dance of continuously flexing metal. To truly grasp how engineers are perfecting this mechanism, we're going to break this explainer down into 5 clear steps. We'll start inside robotic joint precision, then look at the gear distortion problem, how we go about reshaping the gear teeth, modifying them in 3 dimensions, and finally putting those gears to the test. Let's get right into it.
All right, Part 1. Inside robotic joint precision.
So, for decades, engineers actually relied on this theoretical design called the rack approximation method. It basically simplifies all that complex flexing motion by imagining the gears as 2 infinite flat racks just moving back and forth. Now, this assumes a perfect, theoretical ideal where the radial deformation coefficient, which we call K, is exactly equal to 1. This K coefficient defines the shape of that elliptical wave generator stretching our gear, but here's the catch. The mechanical reality is that K is almost never exactly 1. It's constantly shifting. And when K doesn't equal 1, well, that beautiful mathematical tooth profile totally breaks down, and that causes some severe distortion in the gear's trace curve. You end up with these weird, gentle slopes and twisted profiles that, honestly, just cannot work.
Which brings us to Part 2, the gear distortion problem.
Now, what's really interesting about this slide is how it highlights the dramatic stakes when physical reality refuses to match our math inside a high-speed robotic joint. We're looking at the 2 ultimate villains of gear meshing here, the ones actively destroying robotic lifespan and accuracy. Villain number 1 is interference. This is a violent clash where the convex tips of the flexible teeth literally smash directly into the convex tips of the rigid teeth. Ouch. On the flip side, villain number 2 is disengagement, where the flexible teeth just slip right out of the concave roots of the rigid teeth. And both of these, they cause massive stress, rapid wear, and those jerky robotic movements we absolutely do not want.
Let's look at how we fix this in Part 3, reshaping the gear teeth.
To fight back against those villains, engineers came up with a brilliant 2-dimensional solution known as parabolic tooth modification. It's basically subtly shaving down the gear profiles. But you gotta ask, which gear do you actually modify? Well, modifying the flexible inner wheel actually ruins the continuous meshing cycle, mostly because that flexible tooth is constantly engaging with entirely different parts of the rigid gear. So instead, the fix is to exclusively modify the rigid wheel. Shaving down the rigid wheel's tip prevents that nasty interference, and modifying its root completely stops the disengagement. You basically leave the flexible wheel completely alone, which allows it to mesh perfectly across that newly modified rigid surface. It's super clever.
Let's move to Part 4 and see how this builds into modifying in 3 dimensions. You see, fixing a flat, 2D profile is really just the beginning, because these gears actually have depth. To visualize why we absolutely must modify in 3D, just think of a simple plastic drinking cup. The flexible wheel bends exactly like that cup. Under the pressure of the wave generator, the front opening of the cup stretches way out into an oval, but the base of the cup, it remains rigidly anchored in a perfect circle. Because of this cup shape, that radial deformation coefficient we talked about earlier is totally different at the front of the gear compared to the back. If you take a 2D fix and apply it evenly across the whole gear, you are going to get a disastrous collision at the front edge, where the stretch is at its widest. No way around it.
So to solve this headache, researchers developed a pretty flawless 4-step mathematical solution to apply across the entire 3D longitudinal axis of the gear.
Step 1, they discretize or essentially slice the flexible wheel into n number of sections from front to back. Step 2, they calculate the exact radial deformation for each specific slice using the straight generatrix theorem. It sounds fancy, but it's basically a highly complex geometric calculation. Step 3, analyze the meshing motion for every single slice. And finally, Step 4, they determine the absolute minimum amount of radial modification needed for each section just to maintain a tiny uniform gap or backlash between the teeth. We aren't just filing down a gear here, we're literally custom tailoring a 3D spline.
And that brings us to our final chapter, Part 5, Putting Gears to the Test.
Okay, so we've done the math, and we've theoretically designed the perfect 3D tooth profile. Now, using some seriously powerful simulation software called Abacus, researchers put these modified gears through rigorous virtual trials to see if this whole comprehensive solution actually holds up under real-world robotic loads. And this brilliantly illustrates the results. Take a look at that middle row. They tested 3 different radial deformation coefficients, and the design with a coefficient of k equals 1.2, it is the undisputed champion. It gave us the lowest maximum contact stress. In plain English, that means the metal is under far less destructive pressure, which is going to vastly extend the life of the robot. But the real victory here lies in this incredibly satisfying number, 16. In that optimized k equals 1.2 design, a maximum of 16 teeth are perfectly engaged and meshing on one side at any given moment, with absolutely zero interference. That is huge. Because the more teeth you have sharing that load, the more powerful and remarkably precise the robotic joint becomes.
So the crucial point is this mic drop physical rolling test. They built an experimental prototype and ran it for 800 hours. On the old, unmodified gears, only the tiny little tips of the teeth showed any contact. But on these newly modified gears, the contact pattern massively expanded to cover 43.8% of the entire tooth surface. I mean, think about that. Almost half of the physical tooth is now perfectly transferring power, which completely eliminates those dangerous stress concentrations that cause robotic failure in the first place.
Which leaves us with this final, really provocative thought. How will this microscopic gear math revolutionize the next generation of industrial automation? When we think about the macro future of robotics, the robots that are going to build our homes, perform our surgeries, or even explore space, their success literally relies entirely on these invisible, microscopic engineering improvements. By mastering the 3D deformation of metal and reshaping just a fraction of a millimeter of a gear's tooth, we are unlocking a completely new era of precision. So the only question left to ask is, what incredible machines will this new math allow us to build next?